were they the same? All right, let's take a look at that then. When sodium iodide solid is added to an HI solution, the pH, what did you put for this? Unchanged, yeah. It's a strong acid. I'm sorry? It's on Canvas? Yeah, I forgot when I posted this. When did I post this? Over the weekend, yeah. Okay. It's under assignments, though. I didn't put it under discussions. So I thought it would be more visible under assignments than some people don't check the week discussions. So I had people asking me where the quiz was when it was in the discussion section. Oh, it's not due today. It just this is a question about the quiz, number 1 and number 2. You still have lots of time to do it. Number 2, when you log into Canvas, does it show you a new assignment has been posted or it doesn't? I thought it automatically would show you that new assignment is posted or something. No? Oh, okay. I don't know. Maybe I'll post it under announcements. Is that better? If I do post it? Gets a notification for announcements. Yeah, under announcements. Maybe next one I'll post under announcements. When sodium nitrate is added to HNO3, this is the same thing. HI is a strong acid, HNO3 is a strong acid. So it's unchanged. However, that's because these are strong acids. What if you have a weak acid? If you have a weak acid, what happens when you add its conjugate base? Well, if you have a weak acid and you add conjugate base, the pH cannot decrease because decrease would be making it more acidic. You're adding base. If you're adding base, it's got to go up. It can't go down. So, yeah, essentially there's no difference between these two. Okay, other questions?
So this will be due after we complete chapter 18, right?
Yeah. This will be due after we complete chapter 18. Normally it's due the following week, but we have spring break in there, and so this is going to be due after spring break. So I'll try Kenji's suggestion here to try OneNote and see if that doesn't crash on me. But what we're going to do is we're going to continue the titration curve here. Thicken it this line. Where did we leave off last time? Can somebody remind me? Did we calculate the pH like 1 drop after? And then did we calculate the pH like 10 milliliters after, like at 30 milliliters?
I think we were working on the one drop after.
One drop after? All right. Did we finish that one or we hadn't finished it?
I think we were in the middle of it.
We're in the middle of it? Okay. So we're doing plus one drop past the equivalence point. And so this would be equivalence point plus one drop of sodium hydroxide excess. And so once we hit the equivalence point, then we'll add another drop here and see how much the pH climbs. It depends on how steep this curve is. You know? If this curve is quite steep, then the pH will increase significantly. If it's not so steep, it will increase less significantly. And so we're going to estimate the volume of one drop. And the volume of one drop, this is not super precise or super accurate, but it's around 0.05 milliliters. And the reason is the drop size depends on the surface tension. The surface tension depends on what solute you have dissolved in there. So some things will have a stronger surface tension, creating a bigger drop. Other things will have a weaker surface tension, creating smaller drops. And so it's just a rule, it's not a law. And so we're just going to estimate this. It's hard to see the cursor. Estimate. If I can make that a little bit bigger. Do that later. And so did we already do solution dilution? Have we completed that? We did. Did we do step one? Are we just solving for pH right now? Or what are we solving for?
I have step one and like the first letter rise table written out.
Oh, okay. All right, so we'll go to step one, which is the acetic acid plus the sodium hydroxide. This is going to give us sodium acetate plus water, so just salt and water. This salt is not a neutral salt, you know. Sodium acetate is what we call a basic salt. And so if we're looking at these, the addition of HI is a neutral salt, and so it's not going to have any impact on the sodium acetate. And HI3 NaNO3, which is a neutral salt, so that's not going to have an impact. But if we're going to add sodium acetate, it's going to have an impact. The pH should go up because sodium acetate is a basic salt. And that means that the equivalence point, we calculated around a pH of 8 to 9. So around pH 9 is the equivalence point. And so let's see how much higher we go with one drop past the equivalence point. And so the acetic acid concentration is going to be just HAC initial after solution dilution. And then we have the sodium hydroxide initial after solution dilution. And then sodium acetate, we have zero of this. And so we need to know which one is the limiting reagent. And so that means we're past the equivalence point. This has got to be the limiting reagent. And we have excess sodium hydroxide. So if this is a limiting reagent, we're going to consume all of it. So this is going to be minus HAC initial. This is going to be minus HAC initial. How do I know that? How I know that is because we're one drop past the equivalence point. Limiting reagents is always completely consumed because K for this is very, very large. If K was not, then we don't know. But we know that because this goes to completion. And if it goes to completion, then what that means is the limiting reagent is completely consumed. Okay, so that's how. The question was, how do we know that the limiting reagent is completely consumed? And It's only because this K is very large. Minus HAC initial plus HAC initial. And so this sodium hydroxide is going to be whatever sodium hydroxide we started with, which is going to be excess. And then we're going to use enough to neutralize the acid, which is going to be HAC initial. And then we're going to generate HAC initial product conjugate base. So this is a solution of a strong acid and a weak acid. Boy, I can't see the cursor so well. Strong acid, weak acid. And the strong acid is going to be the primary producer of hydroxide. So this is the primary source of hydroxide. And this is going to be the secondary source. And the secondary source of hydroxide is often negligible. In comparison to strong base. Sodium hydroxide is a strong base. Acid is a weak base. So strong bases didn't dominate the hydroxide production space. And the tertiary source of hydroxide would be what? Right, Kw. So just say the third source of hydroxide would be Kw. Normally what we do is the weak base, if we have a strong base, weak base mixture.
Did you mean to write strong acid or strong base up there?
I meant to write strong base. My brain is not working very well today. This morning I made lots of mistakes. Strong base plus weak acid. No, not weak acid. Strong base plus weak base. I think what's throwing me off is HAC is an acid, but HAC we're only using for the concentration. It's not the identity of this because this is actually the acetate concentration. And so that threw me off looking at that. And so I have to be careful. HAC is just the concentration. And so I really should write this out completely. The concentration of sodium acetate will be equal to the concentration of HAC initial. HAC initial we got from before. Therefore we can figure it out. But I'm not writing it all out here, so just try to keep it. So this is weak base. So strong base, weak base mixture. When we have a strong base, weak base mixture, the primary source of hydroxide is going to be the strong base. Usually what that means is the secondary and tertiary sources are negligible. And so the weak base is usually a negligible contributor. And Kw often are negligible. Okay. Try that again. Because K is small, and the common ion effect. The common ion effect would be like Le Chatelier's kind of inhibition. The more product we have, and we're going to have product from the strong base, the less forward reaction we expect, the more it gets pushed to the reactant. And so we have two choices here. I say often, but it's not always, because it depends on how much strong base we have. If we have a negligible amount of strong base and a significant amount of weak base, then it could be flipped. That is, the weak base could be the predominant producer. We've seen this scenario pop up when we've had a negligible amount of strong acid, like HCl, and a significant amount of water, KW, and we see it's flipped. The strong acid ends up contributing less than the weak acid, water. It depends on the concentrations, though. And so what we can do is we can stop here and ignore the KB for the weak and KW, saying it's negligible. Why did I do it like this? I know, did we already calculate the concentrations? Yeah?
We did the concentration of HAC initial.
Mm-hmm.
But that's about it.
Okay. All right, so we'll do HAC initial. I'm thinking, why don't I put numbers in here? Thinking because I didn't calculate the concentrations, but what was the concentration of HAC initial? Okay, thanks. And the concentration of NaOH? 500,624. Okay. Here we can see we have excess base, more base than acid. And so what I'm going to do is I'm not going to carry this many digits because this is going to take too much time. So I'm going to go 4 digits here. But I'm not going to round it because I'm only allowed one rounding step at the end. And so we'll just do 4993. I know I'd like to round it up, but that would set off a cascade domino effect of rounding, which I don't want. And so I just wasted time here. I could have put the numbers in here. Let's see. Let me try to get another page going here.
It's usually just one infinite page.
All right. I guess if I keep writing, it'll probably go down. Okay. So after that, let's put in HAC initial. It's 0.04993. Molar, plus the sodium hydroxide initial, which is 0.05. Ashley, can you tell me what? 0.006. Okay. 0.05006 molar. Sodium acetate initial is going to be 0 molar. And water we omit. All right, now it's easy to see what the limiting reagent is. What's the limiting reagent? Acetic acid. This is going to go to 0 molar. And then we're going to minus 0.04993 molar, which is going to give us 7 and 6 is 13. It's going to 0.00013 molar left. And so we just have a slight excess of sodium hydroxide, and this is going to be plus that. And so this is going to be minus this thing here plus this. So we're going to get 0.04993 molar here. when I look at it, is my assumption still valid? When we have a mix of strong base and weak base, then the primary hydroxide contributor should be the strong base. But when you look at the concentration is lopsided. We have lots more of the weak base than we have the strong base. And so when does the equation switch? That is, when do I have so much weak base that the strong base is negligible? It looks like it's kind of here in this case because, I mean, this is 0.0001, and this would be like 49, so I have like 50 times more weak base. At 50 times more weak base, shouldn't the weak base be the primary contributor of hydroxide? And we ignore the strong base? And surprisingly, it turns out, no, the strong base is still going to be the dominant producer because the Kb for acetate is quite small. The Kb for acetate is 10 to the minus 10. And having a Kb of 10 to the minus 10 means we aren't going to see much. And so even though this looks terribly lopsided, the hydroxide is still the primary producer, so I'd probably still stop here. And so in most cases, that's going to be correct. The only case where it wouldn't be correct is if you're looking at extremely small concentrations of hydroxide. What would qualify as extremely small concentrations of hydroxide? This doesn't quite qualify because this is 10 to the minus 4. At what concentration of hydroxide would I start worrying about things like Kb of the weak base and Kw? Probably not even 10 to the minus, I probably wouldn't start worrying until I get to like 10 to the minus 7, 10 to the minus 8, then I'd start to worry, but this is like, and so I'm not going to worry about it. If I'm ever uncertain, I just kind of next step. And so we can do both ways and see if the acetate does indeed make a negligible contribution of hydroxide. And so we're going to try this in two ways. The first way is I'm going to stop here and I'm just going to ignore Kb and Kw, saying I expect them to be negligible. And so stop and assume Kb and Kw are negligible. All right, therefore the pH is equal to 14.00 minus the pOH. And so we have to calculate the pOH first. The pOH is going to be the negative log of the hydroxide concentration, which is 0.00013. What does that come out to here? Um, 3.795. 3.795. I'm going to carry one extra digit beyond. This would be 2 sig figs here, plus 1. And therefore, the pH is equal to 10.204. And so, what can somebody remind me what the pH at the equivalence point was? It's like 8.23 or something like that. Did we calculate it? Or maybe we didn't calculate it? I don't remember. 8.72. That sounds right. And then we add one drop, and what happened to the pH? The pH jumps to 10.20. So plus one drop, we're at 10.20. All right. I would check, how can we check the answer? check the answer by doing another calculation. Okay, that's one drop. Let's go equivalent point plus 10 milliliters of sodium hydroxide. So what that means is we're going plus 30 milliliters of sodium hydroxide total. Did I already do this calculation? Or not? I don't remember if I did this. No? Okay. So we're going to start off with step I, which is going to be plus 30.00 milliliters of sodium hydroxide into our original 20.00 milliliters of acetic acid. And then we'll do our solution dilution. And so the new concentration of acetic acid, HAC, this will be the initial for step 1, is going to be a 20. Actually, what I'm going to do is, I know I have 4 sig figs for the volume and I have 3 sig figs for the concentration. I'm just going to mentally keep track of that. And so it's going to be a 20 to 50 dilution, total. And so 20 to 50 dilution of 0.1 is 0.04. And I'm allowed 3 sig figs here, so I'm going to go 0.0400 molar. And then the sodium hydroxide is a 30 to 50 dilution of 0.1. Which is 0.0600. And so we have excess strong base here. Oops, I forgot to do one thing. Let me do that here. We'll do another calculation with KB here. If I did it with KB, then I'm just going to look at the acetate. The sodium is a spectator, and so it's going to be acetate plus water. That's going to yield acetic acid plus hydroxide. The initial acetate that we're going to get is 0.04993 molar water, leave out. Acetic acid, 0. And hydroxide, 0.00013. The KB for this, we calculated earlier, it's 5.55 times 10 to the minus 10. It's quite small. And so because of the common ion effect, I expect the change to be very small. So doing this calculation, I'm just going to say etc. shows KB is negligible. So if you weren't certain whether you could ignore KB or not, just do it. And then complete the ice table and see how much additional hydroxide you get from this step, step 2. Okay, we're going to go back to this here. So we complete the solution dilution. We're left with 0.0400 molar acetic acid plus the sodium hydroxide of 0.0600. This is going to go to sodium acetate at 0 and water. Limiting reagent is the acid. So limiting reagent is going to be completely consumed. We're going to lose 0.04 out of 0.06 gives us 0.0200 left over. And we're going to generate 0.0400 molar here. And so we have strong base, weak base mixture. We're going to assume the weak base is negligible contributor. And therefore, the POH is equal to negative log of 0.0200. (00). 1.698, and therefore the pH is equal to 12.301. Okay, again, we ignored the weak base. In the strong base, weak base mixture, the strong base dominates unless the strong base were extremely dilute. And so here at 30 milliliters, we are going to be all the way to 12.30 pH. And so these are typical titration calculations. Now, what we're going to do is, I want to figure out, with a pH of 11, let's go with pH of 11.00, how many milliliters of sodium hydroxide are required to hit pH 11? I can figure that out from the graph, maybe, if I have enough data points here. I don't have enough data points here to really figure it out from the graph. Because if I look, I have a data point here at 10.20. Oops, do this a different color. I have a data point here at 10.20, and then I have a data point here at 12.30. I don't know how this curves, Is this a straight line? No, it's not a straight line. How steeply does this rise and where does it flatten out? We don't know how to draw the curve here. And so it's not resolved enough. So this is what we call low resolution, or we don't have enough data points. Collecting enough data points is a big issue in science. We need to resolve the structural features. In order to resolve the structural features, we have to collect lots of data. And so we need high resolution. We can't have a pixelated image of our titration curve. It's going to be difficult to pinpoint things with. And so, of course, I can calculate a lot more points, but it would just be faster not calculating a bunch more points. It would be faster just to calculate, the volume at that. And so let's try this calculation here. And so this will be the next example calculation, which will be how many milliliters of sodium hydroxide in order to get the pH to equal 11.00. All right, the first thing we have to worry about is what region of the titration curve are we in? And so need to determine the region of the titration curve. If the equivalence point is at pH 8.72, then this is past the equivalence point, which means it's in the excess base region. And so this is the excess base region. That's going to dictate how we set things up. And so it seems like we got to work backwards now, because the previous calculations, we started with the volume and worked forward to the pH. Now we're starting at the pH and we need to work backwards to the volume, correct? Well, what I find is working backwards is more difficult than working forward. And so what I'm going to do is I'm just going to work forward with this. In other words, I'm going to start at step I here. In step I, we need to know how many milliliters of sodium hydroxide. I don't know. So what I'm going to do is I'm going to call that X milliliters of sodium hydroxide. That's how much I'm going to add, X. I know how much acid I have. It's still the same, 20.00 milliliters of acetic acid. One thing I do with all titrations is I always start from the beginning. I never start, let's say, I'm past the equivalence point, so shouldn't I start after the equivalence point? No, I'm going to start at the beginning with the total sodium hydroxide, not with the sodium hydroxide I add after. However, it depends. Some people will do the sodium hydroxide after, which the book does. You can do that too. With millimoles, it's not too difficult, but I don't bother doing it that way. And so for step I, this is what we're going to have. The total volume, I don't know what the total volume is. I just know it's 20.00 plus X milliliters. It's my total volume. And then I'm going to calculate the new initial concentration of acetic acid. And what I mean by initial is before reaction. And so this is right before reaction. I'm going to have an acetic acid concentration of 20 over 20 plus X. I'll just keep track of sig figs in my head. Times 0.100 molar. Or 0.1. And then my new initial concentration is of sodium hydroxide is going to equal X over 20 plus X of the 0.100 molar. Okay, now what I'm going to do is I'm going to move on to step 1. I don't want to write this fraction over and over, here. I don't want to write out this equation. And so instead, I'm just going to use this as my unknown. And so I have my HAC, and my initial concentration is just going to be HAC initial plus sodium hydroxide. And my initial concentration of sodium hydroxide is just going to be NaOH initial, whatever that is. We don't know. These are two unknowns here. And this is going to give us sodium acetate plus water up here. Sodium acetate initial, I know what that is. It's none because this is initial before reaction. No reaction's taking place. Oops. All right, the change. Now, this is why we need to know what region of the curve we're in. Because if we're in the excess acid region, then what's a limiting reagent? Well, if the acid's in excess, the limiting reagent is the strong base. And that throws us in the buffer region for step 2. But for this, we're in the excess base region. That means the limiting reagent is acetic acid. And the limiting reagent is going to be consumed because K is very, very large. And so we're going to go here. We're going to lose all of our limiting reagent. So we're left with 0 molar here. How much sodium hydroxide? Well, the amount of sodium hydroxide we're going to lose is the amount that was required to neutralize all our acid. And so the amount of sodium hydroxide we have at the end is the sodium hydroxide initial minus whatever was used to neutralize the acid, HAC initial. And then how much sodium acetate are we going to generate? We're going to generate plus the same amount. So this is minus this amount. And so the amount of sodium acetate we generate is going to be equal to the amount of acetic acid that was converted into sodium acetate, which is all of it, basically. And so this gives us the hydroxide concentration after step 2. At the end of step 2. Um, so the total hydroxide concentration is going to equal the hydroxide concentration at the end of step 2 plus any hydroxide that's generated by the acetate, the weak base, Kb, plus any hydroxide that's generated from Kw, from water, Kw. What we're going to do is we're going to do the same thing. We're going to assume that the Kb and the Kw are negligible based on previous calculations. So we're just going to assume negligible. And that's a pretty good assumption as long as the hydroxide here is not like 10 to the minus 7, 10 to the minus 8 molar or smaller.
So, for a question like this, how close to the equivalence point would you need to be looking at in order to not assume that we're dealing with negligible values for
Less than a drop.
less than a drop?
Yeah, and how often are you going to calculate less than a drop? Well, maybe a half a drop is still okay. We're talking like 1/1000th of a drop or 1/10,000th of a drop. And so it's kind of ridiculous in that. The green zone that I have is, even though the green zone looked big, when I scratched in the green, the volume-wise, it's extremely small because it's so steep, and so big change in pH results in tiny change in the volume, but tiny change like a tenth, not a tenth, like 100,000, 10,000th of a drop, So we don't really worry about it.
So you wouldn't give us a problem that's like...
No, I wouldn't, because it just doesn't make sense. If you're doing a titration in practical purposes, would I ask you about 1/10,000th of a drop? No. However, you might think, okay, if that's not really sensible, then why am I asking you to calculate the pH of 10 to the minus 8 molar HCl? I'm asking you to calculate the pH of 10 to the minus 8 molar HCl so you can see that it's almost like pure water. And so if somebody says, if there's a challenge, I'm going to drink hydrochloric acid, a strong acid, and they're drinking 10 to the minus 8 molar, it's not fair. That's not really. But you shouldn't drink hydrochloric acid. You definitely shouldn't drink hydrochloric acid, but we already drink hydrochloric acid. If you drink tap water, if you drink tap water, chloride is present. And the pH of tap water is less than 7. And so you're drinking hydrochloric acid. Even mineral water, probably contains chloride. I don't know what minerals they put in mineral water, or if they're natural minerals, or they just put minerals in for flavor. Chloride doesn't have any flavor, though. So if they're putting chloride in there, it might be a waste, of mineral. Sodium does have flavor. Sodium ions. Well, anyway, getting back to this, okay. We want the pH of 11, right? Which means the POH is equal to what? 3. Which means the hydroxide ion concentration is equal to, this is the total, is 1.0 times 10 to the minus 3 molar. Which means we're going to substitute here, which means that the hydroxide ion concentration total, we're assuming, is the sodium hydroxide concentration initial minus whatever was consumed by the acetic acid here. But now we have 2 unknowns and 1 equation. And so we're going to substitute. So we have 2 unknowns, 1 equation. We're going to substitute this. The sodium hydroxide initial after solution dilution is x over 20 plus x minus the acetic acid concentration initial is 20 over 20 plus x. And so this is going to give us x minus 20 divided by 20 plus x. And this has got to equal 1.0 times 10 to the minus 3, which is equal to, I'm going to get rid of scientific notation here. Oops. And I'm just going to call this 0.0010. And I'm going to ignore sig figs here to make the algebra look cleaner. And so this is going to be x minus 20 equals, and then I'm going to multiply both sides by 20 plus x. And so this is going to be 20, this is going to be 0.02 plus 0.001x.
Oh, do we still need the point ones for the initial? The point one.
Yes, we do. We need the point ones here. I forgot that too. We need the point ones, good point. And so I better not forget it here. I'm going to factor it out. Okay. It's 0.1. All right, so I need to divide by 0.1. This is 10 to the minus 1, so I'll bring that up. 10 to the positive 1, 10 to the minus 2. Okay, so this is times 10 positive 1, which is going to equal 0.01 rather than 0.001. Okay, does that work okay now? And so if that's 0.01, so 20 times 0.01 gives me 0.2. And then this should be 0.01x. Okay. And then I'm going to subtract 0.01 from both sides. If I subtract 0.01, this 1 minus 0.01 gives me 0.99x. And then I'm going to add 20 to both sides. So this is going to come out to 20.2. And then x is equal to 20.2 divided by 0.99. 20.2 divided by 0.99. 20.404. And therefore we're going to have 20.40 milliliters of sodium hydroxide required to reach pH 11. So let me go back on here. So we need 20.4, so I'm way off in my estimate here. It's closer to here. And we'll hit pH 11 here at 20.40 milliliters, 11.00.
So do you recommend dropping the decimal points when you're doing your calculations? Because I got something that's close but like a little bit different.
I'm just dropping the zeros.
I'm dropping
The zeros at the end. What did you get?
I got 20.04.
20.04?
Yeah, maybe I did something wrong.
No, you could have been right. Maybe I did something wrong. Did anybody else get 20.04? The way this is the way I recommend checking the answer. Some things it's hard to double check this, but this one we can double check this. The way we double check the answer is we just repeat the calculation with this volume. By repeating the calculation, using this volume. Okay, so this is going to be the double check here. And the situation is this. Usually you want to check your answer, and normally what do? You look in the solutions guide. But pretty soon, there's not going to be any solutions guide. And you have to figure out whichever way you can, if you can have confidence in your answer. And so this is the way we're going to try to see if we have any confidence in this answer. We're going to repeat the calculation in the forward direction. And it should be a pretty quick calculation, hopefully. So we're going to do plus 20.40 milliliters of sodium hydroxide. My number could be way off, but we'll see it here because we won't get the correct pH. And we're going to add this to 20.00 milliliters of acetic acid here. So we'll go ahead with this here. And so this is going to give us a total of 40.40 milliliters of solution. And then we're going to calculate the new acetic acid concentration, which is going to be a 20 to 40.4 dilution of 0.1 molar. Here I'm going to eliminate the extra digits, but the extra digits that I'm dropping are all zeros. So the only reason I'm doing that is just to save a little bit of time writing this out, especially during exams. It could be critical to save a little bit of time. But I'm going to carry extra digits here. I'm not going to round this. So this is going to come out to 0.0495. We'll just carry one extra digits here. Molar. And then we're going to go to the sodium hydroxide. The sodium hydroxide is going to be a 20.4 over 40.4 dilution of 0.1 molar. And that's going to give us 20.4 divided by 40.4 times 0.1, 0.050, 5049. Let's just do 0.05049. The next digit is 5. So I'm going to have some round off error, but hopefully not too much. All right, now we're going to do our acetic acid plus sodium hydroxide. And this is going to give us sodium acetate plus water. And so our acetic acid is 0.04950. And our sodium hydroxide is 0.05049. And our sodium acetate is 0. And so our change is we're going to lose all our acid. That's the limiting reagent. And we're going to go minus 0.04950 here. So 5049 minus 4950 would be 0.00099. So 0.00099 molar. And then the amount of acetate we have is going to be plus this amount. So this is going to be minus this amount. And so this is going to be 0.04950 molar. All right, we see that the hydroxide is still, this is only 10 to minus 4, so I'm not going to worry about the sodium acetate. And so we could go ahead and calculate the pOH. The pOH is going to be the negative log of the 0.00099. .00099 log, and I get a pOH of 3.004, which means the pH is what? 10.996, which is rounding to the correct number of sig figs. We're allowed 2 sig figs Is that correct? Are we allowed 2 sig figs? Yeah, we're going to be allowed 2 sig figs because of the subtraction here. Do you see that? Actually, I'm carrying more. I'm probably not even allowed 2 sig figs. I'm probably allowed only 1 sig fig. Because this should only be three sig figs here. So if I have only 3 sig figs here, then I'm only allowed 4 decimal places. But if I have allowed 4 decimal places, it is going to round up to 0.010. So that still gives me 2 sig figs. So I'm going to go with 2 sig figs in my final answer. And so rounding this to 2 sig figs, I'm going to get 11.00. So the double check did work, and so if you double check yours, it may not. So double check yours and see. Okay. And then this looks good. Yeah. Okay. Yeah, I forgot the 0.1, so we probably should rewrite it. Yeah. So that's why this 0.02 is wrong. Let me erase that. So x minus 20 is equal to 0.2 plus 0.01. I multiplied by 0.01. This is wrong. Yeah.
Or like originally on top where you had one, but it felt point oh one.
No, what I did was I divided both sides by 0.1. So I factored out the 0.1 and then divided both sides by 0.1. So 1 times 10 minus 3 divided by 0.1 is 1 times 10 minus 3 times 10.
But if you do it the other way we do.
Yeah, then you would distribute it in there. But I didn't want to distribute it in there. You could do it that way too. It's fine. Either way.
Yeah, that's the step I missed.
I'm sorry?
That's the step I missed. I forgot to multiply by 10.
Oh, okay. Yeah, that's what times 10. All right, any questions on this? All right, the next examples we're going to do is it's going to get a little bit more complicated because we're going to try diprotic acid this time. In one way, it's more complicated, in another way, it's just the same. But we have 2 types of diprotic acids that we deal with. The 2 types of diprotic acids are like strong. If you have a strong diprotic acid, an example would be like H2SO4. H2SO4 has a Ka1 of very large and a Ka2 of 0.012. 0.012 is kind of big. This is big for a weak acid. And so step 1 is strong, but step 2 is weak. Normally, when we have a weak acid in the presence of a strong acid, we ignore the weak acid. However, you can't do it with sulfuric acid. In the last case, we just kind of ignored the acetate. We ignored the acetate because the Kd for acetate is 10 minus 10. 10 minus 10 means it's extremely weak. But when you look at this weak acid, the Ka for this weak acid is 10 to the minus 2. 10 to the minus 2 is kind of big. It's kind of big because when you look at the strongest of the strong weak acid, what is the strongest weak acid on this chart? Can you tell me what the strongest weak acid on this chart is? Oxalic acid. It's 10 to the minus 2. Almost 10 to the minus 1. 10 times 10 to the minus 2 is 10 to the minus 1. That's the strongest. And so this is kind of big for weak acid. We'll just say big for weak acid. Therefore, it's significant. If acetate had a KD that big, I wouldn't have ignored that. I would have factored it in. Does that make sense? So it turns out that you get a lot of hydronium from step 1, but you'll get an additional 10% from step 2. So if you ignore step 2 here, your calculation is going to be off because you're ignoring 10% additional hydronium from step 2. However, what if we ignore KW here? Would KW lead to a large error? Not at all. KW is not significant at all. The other type of diprotic will have weak. So what's an example of a weak diprotic acid? Seems like oxalic acid would be an example there, where we have Ka1 and Ka2. Ka1 is like 10 to the minus 2, roughly. Ka2 is what? Ka2 would be the second deprotonation. Look at the top right on our chart. Do you see that species? HOOCOO minus? How would you name that? Hydrogen oxalate, which is 6.4 times 10 to the minus 5. So if I have something like oxalic acid, this is like 3 orders of magnitude smaller, so most likely I'd ignore Ka2 and Kw if I'm just looking at the pH. Because when we begin with Ka, A means acid plus what? Acid plus water. And so if I'm looking at pH, then here, if I'm looking at pH, I'd consider both of these. Here, I'd probably only consider Ka1. And so that makes a difference in how we start our titration, because when we start our titration, we write the initial pH before any sodium hydroxide has been added. And so this will be at 0 milliliters of sodium hydroxide. This will be milliliters of sodium hydroxide on the X, and then the pH over here. And so we're just going to calculate the initial pH and this will just be oxalic acid. And we'll have Ka1, Ka2, and Kw. And here we're just going to assume that Ka2 and Kw are negligible. Just look at Ka1. Should be enough. And then what should happen is, okay, once we start neutralizing it, then we're going to be in the buffer region. When we have a strong acid, we're not in the buffer region. Because a buffer is going to be a weak acid plus its conjugate base. If we have a strong acid plus its conjugate base, that doesn't qualify as a buffer. Because the conjugate base of a strong acid is so weak, considered neutral in terms of base properties. So this excess acid region here in step 1 will be a buffer in step 2. And so step 1, excess acid. Step 2, we have a Henderson-Hasselbalch buffer, HH buffer. And we call this region buffer 1. This is before we hit the equivalence point. And so let's come up with a scenario here. We need some numbers here to get some volumes. And so what we're going to do is we're going to take, in this example, we're going to take 0.100 molar oxalic acid plus 0.100 molar sodium hydroxide. And we'll keep the numbers simple, 20.00 milliliters of oxalic acid solution plus X milliliters of sodium hydroxide. And so the first equivalence point is going to come at 20 milliliters. And so we should see a little rise there. And do you know where the second equivalence point is going to come in at? The second equivalence point is we're going to have to add another equivalent of sodium hydroxide. And I picked the molarities here to keep the volume simple. If the molarity is the same, then the volumes are going to be the same. Okay, so it's 20 and 20 here, and then 20 plus 40. That is, I need another equivalent. An equivalent is 20 milliliters, so this can take me all the way out to 40 milliliters here. And so the second equivalence point is going to come in at 40 milliliters. All right, so let's take a look at buffer region 1. So we have our oxalic acid. This is going to be our excess, or no. Yeah, that's right, excess. Plus our sodium hydroxide. Sodium hydroxide is going to be our LR. This is going to produce the salt, sodium hydrogen oxalate, plus water. So what we're going to do is we're going to start off with some initial amount of oxalic acid. And oxalic acid, I don't want to write this formula over and over, so I'm just going to call it OXAC. OXAC is the abbreviation for oxalic acid. Sodium hydroxide, I don't mind writing that one. It's not too difficult. And so I'm going to start off with initial concentrations here after solution dilution. So I'll do step I. And then I'm going to lose my limiting reagent here. So this is going to be minus the sodium hydroxide initial. This is going to be minus the same. This is going to be plus the same here.
So, quick question. For that first reason, you were saying that it doesn't count as a buffer because the conjugate of a strong acid is negligible, or can you say?
Yeah. Here, if I were titrating sulfuric,
Gotcha.
then there's no buffer 1. There's no buffer 1 region because when I have a mixture like on the quiz here, some people will say that this is a buffer. This is another question I have. Is a sodium iodide hydriodic acid solution a buffer? True or false? And so I have sodium iodide and hydroiodic acid. Looks like a buffer solution because I have an acid-base combo. But this acid-base combo is not a buffer solution because it's a strong acid and a neutral salt. And so a sister question to this, which I'm sure I've asked many times, is this a buffer solution? In fact, maybe I asked it on this quiz here because that's sort of asked it on this quiz, but not really. A 1-to-1 mixture of nitrous acid and sodium nitrite, that is a buffer. This is a Henderson also buffer. So, at the half equivalence point, that is a 1-to-1 mixture of H is equal to pKa. Talk about. This is what you do, and this is what I would do, since you have a lot of time for this. I would do this quiz, and then I try to predict what kinds of questions might appear on the test by coming up with every single variation I can think of for these questions, basically. That's what I do preparation for exams. And then I look at the homework and think, okay, what types of questions, variations can I see? And that's why I like to see as many variations of problems as possible. That way, there are fewer surprises when it comes to tests. So at the end of this, initial change. At the end of this, I'm going to have my oxalic acid minus however much sodium hydroxide I had there. And then I'm going to have 0 sodium hydroxide left over. And then how much hydrogen oxalate? How much hydrogen oxalate I'm going to have is going to be equal to how much of the acid I've neutralized here. And that acid that was neutralized is converted into product. And so that gives us the same concentration of sodium hydroxide. And so what we have here is we have oxalic acid and its conjugate base, sodium hydrogen oxalate. And this is the HH buffer. And so if we go to the half equivalence point, the half equivalence point would be half of this, which is 10 milliliters. So example, at the half equivalence point, ignore this little e here, we've neutralized half our acid. And so the pH is equal to pKa for oxalic acid plus the log. If we've neutralized half, then that half was converted into product. And so this gives us the half equivalence point, leaving 1/2 of it unreacted, excess left over. So we've neutralized half and we have half left over. So the base product is half, the acid remaining is half. And therefore the pH is equal to the pKa for oxalic acid. And the pKa for oxalic acid is the negative log of the Ka, which is equal to the negative log of the Ka of the oxalic acid, 0.059. Off this chart may not be the most accurate, but we're just going to use it. And so 0.059, 1.229. $1.23. And so this calculation is easy. This is 1.23. There are 2 more calculations that are super easy. What are they? The 2 more calculations that are super easy are the 1/11th equivalence point. Do you remember what the pH should be at the 1/11th equivalence point? This is the half equivalence point.
Is it 1 minus the...
Yeah. And so it should be 1.23 pKa minus 1. So at the 1/11th equivalence point, pH is equal to pKa minus 1. Where does the minus 1 come from? The minus 1 came from the ratio. The base to acid ratio is 1/11th base. How many parts acid are left over? If I'm 10/11th acid, which means I have a base to acid ratio of 1 to 10. The log of 1/10 is minus 1. And so this has a pH of 1 minus 1.23 gives me a pH of 0.23. 0.23, think about that pH. It's a weak acid. What do you think about that pH? It's really low for weak acid. I mean, 0.23. In fact, that low of a pH, I start to worry about. That low of a pH has me thinking, what pH must I have started with? Because this is at the 1/11th equivalence point. The 1/11th is, we just neutralized 11 parts of this. So we take 20 and divide it into 11 parts. So 20 divided by 11 gives us 1.818. So this is at 1.18, or no, 1.8, sorry, 1.818 milliliters. So this is 1.818 milliliters. I'll just say 1.81 milliliters. 1.818. I better put in the 8. In other words, 1.82 milliliters. This is 10/11th, or 1/11th. The other point that's easy to calculate is the 10/11th equivalence point. At the 10/11th equivalence point, we're at, if we neutralize 10 out of 11 parts, we're going to be at 18.18 milliliters. What is the pH? The pH is pKa plus 1, and pH should be 2.23. So when you guys were doing the titration, it depends, how concentrated you can make this. In order to see these very low pHs, it has to be very concentrated. Although buffers, remember, the ratio stays the same, but you could dilute it. You could dilute it up to a certain point, because dilution's not going to change the base to acid ratio, because they're both going to have the same dilution factor. So let's say you did a 1-to-2 dilution. You did a 1-to-2 dilution of the base, which means you're also going to do a 1-to-2 dilution of the acid. So the dilution factor cancels. The ratio stays the same. But in order to see these things, what happens if you did a 1-to-1 million dilution? If you did a 1-to-1 million dilution, are you really going to see these kind of pHs? You dump in 1,000,000 times parts of water, what's going to happen? Eventually, the buffer pH is going to approach pH 7. So this is why when you guys were doing your pH titration, I asked you not to dilute it by 100 unless it was initially very difficult to dissolve your acid. In the procedure, it says to take your solid acid and add 100 milliliters of water. 100 milliliters of water means your pH is going to start off higher than if you used a minimum amount of water to dissolve it. If you use a minimum amount of water to dissolve it, your pH will start off lower. Now, Henderson-Hasselbalch does not care. It just cares about the ratio. So you get the same ratio. A 1-to-1 ratio is the same as a 0.00001 over 0.00001. It's a 1-to-1 ratio. But what that means is this: we might not see these. I mean, that's got to be quite concentrated to get that low. That pH is extremely low. These pH is extremely low. Let's say, what concentration did we start at? What concentration we started at was 0.100 molar oxalic acid. With 0.100 molar oxalic acid, was that concentration low enough to even see these? So we started at 0.100 molar oxalic acid. There's a certain limit. That limit is solubility. Could we have started at 1,000 molar oxalic acid? No, because you can't cram that much oxalic acid into a liter. Even pure water, if you have a liter of pure water is 1,000 grams. 1,000 grams of water is only 55.5 moles. And so even pure water, the max is going to be 55.5 moles in a liter, and that's pure. But anyway, let's calculate the initial concentration. Well, we don't have to calculate the initial concentration. Let's calculate the initial pH of oxalic acid. And so I'm going to do that here. And so what I'm going to do is I'm going to mark these with an asterisk because, well, 1.229, maybe that's reasonable. But for sure, 0.223 seems quite low. And so if we calculate the initial pH of oxalic acid, what do I get? So there's no solution because this is at 0 milliliters of NaOH. But we can skip step I. And then I'm just going to go to oxalic acid. The strongest base presence, water. This is going to give me hydronium and hydrogen oxalate ion. Ka for this is 0.059 off our chart in the room. So the initial is 0.100 molar. Water is nothing. Well, water we ignore. And then hydronium and hydrogen oxalate are 0 and 0. So this is minus X plus X plus X. So at equilibrium, we're going to have 0.100 minus X molar, X molar hydronium, and X molar hydrogen oxalate. This is going to be an X squared over 0.100 minus X. And then I'm just going to go ahead and try the simplifying assumption. This is going to go X squared over 0.100. And then solve for X. X is equal to 0.076. I'm going to try to save some time here, which means we have a 76% change. Too big. And so the simplifying assumption fails. That means we're going to have to use the quadratic. And so I'm going to solve for the quadratic. It's going to be X squared plus 0.059 X minus 0.0059. Are we out of time? Equal to 0. X, let me just tell you what X is since I just solved it earlier. X is 0.05278. 0.05278. And then we'll complete this tomorrow.
Professor, at the beginning of the semester, I think like day one, you said you might be out April 10th.
Yeah, I'm going to be out Thursday. That's correct. I'll announce this tomorrow too. Thursday, I'm going to be out for sure. There's not going to be any substitute. I'm going to post a makeup lecture on Canvas for that, and so I'll just have a makeup lecture talking about the next chapter there. A substitute is going to cover it differently than I want. So
we'll finish chapter 18 tomorrow.
We're going to finish chapter 18 tomorrow. We're almost done. So I'm going to do that right at the beginning class. I'm sorry? Not, next week is spring break. Exam will be after, when we come back from spring break. Wednesday. Monday the quiz is due. Wednesday will be the test.